Good afternoon, everyone. Welcome back in my channel, Dr.Satendra. Dear friends, if you want this type of videos related to mathematics for higher level, then you need to subscribe, share and like my videos and my channel. Today we discuss new topic sequence and series. Now definition of sequence. Definition of sequence. The sequence is what is sequence? The sequence is a mapping, that is a mapping F such that capital N tending to capital R is called a sequence. Of real numbers. Full stop. Sequence is denoted by Fn or Xn or An, where capital N set of all natural numbers, set of all natural numbers, capital R set of all real numbers. Now again, a mapping or a function f such that n tending to r is called a sequence of real number. It is denoted by fn, xn or an, where n is a natural numbers or capital R is a set of real number. N is a domain or R is a codomain, that is range of mapping. Now we can explain by a example. First example, let Fn equal 1 upon n for every small n belongs to capital N, that is set of natural number. Now we can calculate n is equal to 1, that is 1 upon 1, f2 1 upon 2, f3 1 upon 3 up to dot dot. Now fn sequence can be written as 1, 1 upon 2, 1 upon 3, dot dot. Now second example, An is a sequence. This is equal 1 upon 2 to the power n. This is equal 1 upon 2, 1 upon 2 to the power 2, 1 upon 2 to the power 3, comma dot dot. There are two examples of sequence. Now, kind of sequence. Kind of sequences. Number first kind, finite sequence. Finite sequence. A sequence has finite element is called finite sequence. The sequence has finite element is called finite sequence. Example: 1, 2, 3, 5 up to dot 29 equal to 2n minus 1 is the nth term of this, where n equal to 15. Now in this sequence, this is the sequence of odd numbers. The number of in this sequence equal to 15. Therefore, the number of elements in this sequence is a finite number. Therefore, sequence will be finite sequence. Number 2, infinite sequence. Infinite sequence. A sequence has infinite elements is called infinite sequence. Example: 2, 2, up to dot, that is 2 is a sequence, is a finite, is infinite sequence. QUENCE. This is the example of infinite sequence. Number 3, bounded sequence. Bounded sequence. Bounded sequence are two types. Number first, bounded above sequence. Bounded above. A sequence AN is said to be AN is said to be bounded above if there exists a real number capital M such that n is the nth term of the sequence less or equal to m for every n belongs to capital N. Now next type 3.2, bounded below sequence. Bounded below. A sequence AN is said to be bounded below if there exists, if this is the sign of there exists a real number capital M such that an greater or equal to M. That is a sequence an is said to be bounded when it is bounded both above and below. That is, every sequence an is said to be bounded when it has both conditions, bounded above and bounded below. Now we take an example. An is a sequence. This is equal to 1 upon n, closing a sequence sign. This is equal to 1 upon 2, 1 upon 3, 1 upon 4, comma dot dot. Now an greater than 0, less or equal to 1, where 0 is lower bound and 1 is upper bound of sequence. Now this is an example of bounded sequence. Now next type, fourth type. Type number 4, unbounded sequence. Unbounded sequence. The definition of this: if there exists, this is the sign of there exists, no real number. If there exists no real number m, that is capital, such that an modulus lesser equal to m. For every small n belongs to set of natural number, then sequence an is said to be unbounded. Unbounded sequence. We take an example. A sequence. This is equal to 2 to the power n minus 1. This is equal to 1, 2, 2 square, 2 cube, dot dot, where an greater or equal to 1, that is the lower bound of the sequence, lower bound of sequence. There is no upper bound and there is no upper bound, that is an is an unbounded sequence, is a unbounded, is an unbounded bounded. Now next type, point number 5, convergent sequence. Convergent sequence. A sequence an is said to be convergent an is said to be convergent if limit n tending to infinity of an is finite. Is finite. We take an example an equal 1 upon 2 to the power n. Now an equal 1 upon 2 to the power n, then taking the limit n tending to infinity both sides, this is equal to 1 upon 2 to the power infinity, 1 upon infinity, this is equal to 0. Now the limit of the sequence is a finite, that is an is a convergent sequence, is a convergent sequence. Number 6, divergent sequence. Divergent. Next type, divergent sequence. The definition of this: a sequence an is said to be divergent is said to be divergent if limit n tending to infinity an is another term of the sequence is infinite, not finite, is infinite. Then we take, that is, or we can say this limit n tending to infinity an equal plus infinity or minus infinity. The meaning of infinite, that is the limit of sequence n tending to infinity an equal to plus infinity or minus infinity. Now we take an example to explain the divergent sequence. Example first, an is a sequence n square. Now an equal n square, taking limit n tending to infinity both sides, this is equal to plus infinity. Now second, an is another sequence minus n square. Now an limit n tending to infinity, this is equal to limit n tending to infinity minus n square, this is equal to minus infinity. That is there are two examples of divergent sequence. Now, next type of sequence, point number 7, oscillatory sequence. Oscillatory sequence. Next type, oscillatory sequence. What is oscillatory sequence? If a sequence an neither converges to a finite number nor diverges to plus infinity or minus infinity. It is called an oscillatory sequence. An oscillatory sequence. Now again, a sequence an neither converges to a finite number or nor diverges to plus infinity or minus infinity, then such sequence is said to be oscillatory sequence. Please stop. Oscillatory sequence are of two types. Oscillatory sequences are of two types. First type, 7.1, a bounded sequence. Sequence is bounded. A bounded sequence which does not converge. Which does not converge. Bounded but not converge is said to finitely. Such bounded sequence which does not converge, then it is said to be oscillate finitely. Then we take an example. An equal minus 1 to the power n. Now an equal to minus 1 to the power n. Now we take a 2n, this is equal to minus 1 to the power of 2n, taking limit n tending to infinity, both side, this is equal to 1, limit n tending to infinity, this is equal to 1. Now a 2n plus 1, this is equal to minus 1 to the power 2n plus 1, taking limit n tending to infinity, this is equal to minus 1, limit n tending to infinity, this is equal to minus 1. Both are limit exist. The first limit value plus 1 or second minus 1. But do not converge. That is both are not equal. Then we can say limit an does not exist. limit of this sequence does not exist. It is a perfect example of bounded sequence but not converse. That is, sequence is said to be oscillate finitely sequence. Now, second kind, that is 7.2, an unbounded sequence. An unbounded sequence which does not diverge, is said to oscillate infinitely. Then we take an example. An equal to minus 1 to the power n into n. That is, an equal to minus 1 to the power n imply a to n minus 1 to the power 2n into 2n, taking limit and tending to infinity both sides, then we get value of plus infinity. Now a to n plus 1, limit and tending to infinity, this is equal to minus 1 to the power 2n plus 1, 2n plus 1, limit and tending to infinity, then we get value of this minus infinity. This is the example of unbounded sequence, but both limits are not exist or equal. Then we can say given sequence does not diverge. That is, sequence an does not diverge. Next type, number 8, monotonic sequence. Monotonic sequence. Monotonic sequence, there are two types. First type, 8.1, monotonically increasing. Monotonically increasing. A sequence an is said to be monotonically increasing if an plus 1 greater or equal to an for every small n belongs to capital N. Now second, 8.2, monotonically decreasing. A sequence an is said to be monotonically decreasing if an less or equal an plus 1 an plus 1 less or equal to an, comma, for every small n belongs to capital N. If we take a sign only greater, then the sequence is known as monotonically strictly increasing. Or same, we take lesser not equal, then sequence is said to be monotonically strictly decreasing sequence. That is a sequence an is said to be monotonic, if it is either monotonically increasing or monotonically decreasing. Full stop. That is a sequence an is said to be monotonic if it is either monotonically increasing or monotonically decreasing. Now next type, number 9, Cauchy sequence, Cauchy apostrophe s, Cauchy sequence. If an is the sequence of real number, and any positive number epsilon greater than 0, then for Cauchy sequence am minus an modulus lesser epsilon, comma, small m greater n and small n belongs to capital N. Now, limit of sequence. What is limit of sequence? Let L is the limit of the sequence. L, we can consider a real quantity L. Let L is the limit of sequence an. Then there exists, this is the sign of there exists, a positive number epsilon greater than 0 such that an minus L modulus lesser epsilon for every n greater or equal to m and small n belongs to capital N, or we can say limit n tending to infinity an equal to L. This is the complete.